All right, let's try out an example where we actually go through and solve the entire thing. So we're going to be looking at this crate sliding to the right because we're pulling it with 200 newtons. We've got friction opposing that motion. And they want to know how far it goes once 3 seconds have passed. So this is an interesting one because we've got um, a constantly applied force will also have a constantly accelerating situation. So we can use that constant acceleration equation to find its distance and velocity. But how are we going to find that acceleration? Well, we'll need to set our forces equal to mass times acceleration, and that should give us the information that we need. So let's start by drawing up our free body diagram, and we'll need to draw up two of those. Well, free body diagram and a kinetic diagram. Right? So our free body diagram, if we have our crate, it's got its own weight, right, which would be 50 kilograms times 9.81 meters per second squared. Those multiply, give us 490.5 newtons. We'll also have a normal force. We'll have a friction force opposing the motion, so that would be 0.3 for our coefficient of friction times the normal force. And the only other one that they gave us was this angled 200 newtons at 30 degrees from the horizontal. So a very common mistake would be to be like, oh, look, I know my normal force. It's 490.5. Is that the case at all? Please say no. Right? Don't fall for that mistake. It's really easy to do that, right? Because if this was just sitting there, sure, its normal force would be that. But because we're tugging upwards with 200 newtons, 200 sine 30 is going in the same direction, in that y direction, right? So that's going to lessen the normal force. So we'll have to account for that. So don't do that. Here is our kinetic diagram. And if we say that this is the y direction and this is the x direction, we can do the same here. That's our y, that's our x. And right, that could be our center of gravity. We need to draw in our MA for any accelerations that we see here. So what is our acceleration going to do? It's definitely going to slide to the right. So let's put in an MAX. And we got to think, is it going to accelerate upwards? Well, what would have to be the conditions for it to go upwards? We would have to have this upwards component be greater than the downwards weight, essentially, right? So 200 sine of 30, is that going to be greater than this 490.5? No, so we can assume it is not moving upwards. We don't have any AY, it's equal to 0, right? So it's only accelerating to the right. This would be our kinetic diagram. So with those two in place, we're able to jump in here and say, all right, let's sum some forces in the x equals max. All right, and we could sum some forces in the y equals may. Now, if we do the x's, what's going to happen? We'll have 200 cosine 30 to the right and negative 0.3 times the normal force, because that's to the left, equals, that's all our forces. And on the mass times acceleration, we have max. Now, we know what the mass is. We could plug that in. Don't know the acceleration yet, and we don't know the normal force yet. So we're going to have to pause on that one for a little bit, go over to the y equation and solve some more. So in the y direction, what are our forces? Sum the forces in the y. Right? Oh, I forgot my little sum symbol there. Negative 490.5 plus the normal force plus 200 sine 30 equals MAY, but we don't have any AY, right? So that's going to be 0. So this is just the sum of the forces in the y equals 0. Nothing we haven't done a million times in statics. So our normal force we could solve for there, and that would come out to be 390.5 newtons. A little bit funny with normal force and newtons there, but what do you do? So we've now got newtons, or we've got the normal force. We're going to plug that in and solve for a x. So 200 cosine 30 degrees minus 0.3 times that we just solved for. All right, I'm plugging that in right here. Equals the mass, which was 400 kilograms, if I remember correct. No, 50 kilograms for the mass times acceleration x. And with that, we can solve for ax. Ax will come out to be 1.121 meters per second squared. Not quite our answer, but that is very close, right? They asked us for what? Let's look back at it. Find the distance it travels and its velocity. So because this is a constantly applied 200 newtons, that's pretty nice because it means that we also have a constant acceleration in that direction. So we could use our constant acceleration equations rather than integrate to find velocity and position. So the equations that would be useful, right, if we want to find the final velocity v, maybe this one, that guy, right, from our constant acceleration equations. So if we're looking for the final, we could plug in initial velocity of 0, starting from rest, plus 1.121 meters per second squared times t, which they said when t equals 3 seconds. So that'll give us a final velocity at t equals 3 of 3.363 meters per second. There's one answer. We're looking for the final distance that it goes. So let's find s, the position. So we started an initial position s naught plus v naught t plus 1/2 at squared. That sounds like one that we could plug in stuff we know and solve for a position. So the final position would be initial position 0, initial velocity 0, 1/2 a times t of 3 seconds squared. And that would give us our final position of 5.044 meters. All right, that is it for that one. Oh, some crazy double underlines there. That's all we would need for that problem to, looking back through, we drew our two diagrams, and then we set our sum of the forces equal to mass times acceleration. In the y, it was 0, which allowed us to find the normal force. Then we plugged that back in, found our acceleration, used our constant acceleration equations to calculate what the final velocity and position were. So a great example of what we could do with this sort of thing where we set some of the forces equal to ma.